Imagine you're sitting on a train. Beat a very fast train. In fact, let's say it's moving at half the speed of light. You've got a flashlight. You point it forward and you click it on. Here's the question, and I want you to really sit with it before I give you the answer. How fast does that beam of light travel? Your gut says, well, if the train is going half the speed of light, and light goes the speed of light, the beam must go 1.5 times the speed of light from the perspective of someone standing on the ground. That's not just wrong. That answer is magnificently wrong. And the fact that it's wrong, the reason it's wrong, changes everything we think we know about time, space, and reality itself. Before we break physics, let's meet the thing doing the breaking. Light is weird. I mean genuinely, profoundly. Keep you up at night weird. It's not a ball rolling down a track. It's an electromagnetic wave, a ripple in the electric and magnetic fields that permeate all of space. And it has no mass. None. Zero. Zip. Think of it like this. If you shake a rope, the wave travels along it, but the rope itself doesn't go anywhere. Light is a wave in the fabric of reality in the electromagnetic field, and the rope is the universe itself. Except unlike the rope, this field is everywhere, all at once, with no medium you can touch or weigh. In 1865, James Clerk Maxwell wrote down the equations that govern electricity and magnetism, and buried in those equations, like a hidden message, was a prediction. He could calculate the speed at which these electromagnetic waves would travel, and it came out to 299,790,458 meters per second. Newton had given them a beautiful universe, a clockwork universe. Things moved through absolute space. Time ticked absolutely. And if you were on a moving train and threw a ball forward, the ball's speed was your speed plus the ball's speed. Speeds added. It was obvious. It was common sense, but Maxwell's equations gave a specific number for light speed, not light speed relative to the source or light speed relative to the observer, just a number, a constant c, unchanging, absolute. And the question that haunted physicists for 30 years was, relative to what? If I'm on a train moving at half the speed of light, and I measure the beam from my flashlight, I should measure it going slower than you do from the ground, right? Because I'm running alongside it. In 1887, two physicists, Michelson and Morley, built an exquisitely precise instrument to measure exactly this difference. They expected to find light moving at slightly different speeds in different directions as the Earth moves around the sun. They found nothing. Light moved at the same speed no matter what. The universe was not playing by Newton's rules. A young 26-year-old patent clerk in Bern, Switzerland, heard about this problem not from the experiment directly, but from deep thinking about Maxwell's equations, and decided to take the contradiction seriously. What if, Albert Einstein asked, light speed is actually constant for every observer? What if that's not a paradox to resolve, but a fact to accept? And what must change about the universe to make that true? What had to change was everything. Here's Einstein's great leap, and I want to walk you through it the way a good teacher would, not with the math, but with the picture in your mind. Imagine a clock made of light, two mirrors facing each other 1 meter apart, a single photon bouncing back and forth. Every time it completes a round-trip click, that's 1 tick. Now put that clock on a spaceship moving sideways very, very fast. From inside the ship, the photon still bounces straight up and down, 1 meter. Click, no problem. But you, watching from the ground, see something different. Because the ship is moving sideways, the photon doesn't go straight up and down from your perspective. It traces a diagonal path, a longer path. The photon is still traveling at the speed of light. It has to be, but it's covering more distance per tick from your frame of reference. So each tick takes longer. The clock is running slow. Time on the ship is genuinely, physically, measurably passing more slowly than time where you're standing. This isn't an illusion. It isn't a metaphor. We measure this effect every day. GPS satellites orbit the Earth at about 14,000 kilometers per hour. That's fast enough that their clocks tick microseconds slower per day than clocks on the ground due to time dilation. If we didn't correct for this, if we just ignored Einstein, your GPS would drift by about 11 kilometers per day. Your map would think you're in a lake when you're on a highway. Take two twins. Put one on a rocket ship that accelerates to near light speed, flies to a nearby star, and comes back. The traveling twin has aged less. Maybe a year has passed for her. Her twin on Earth is 10 years older. They're the same age at the start. They're not the same age at the end. Time is not a river flowing at the same rate everywhere. It's more like a river that flows faster or slower depending on how fast you're moving through space. The faster you move through space, the slower you move through time. It's as if the universe has a sort of cosmic speed budget, and you're always spending it between space and time. When you spend more on space, you have less for time. Time isn't the only thing that changes. Space does too. If you're traveling very fast, distances in the direction of motion actually get shorter. Not from your perspective, from the perspective of someone watching you. Imagine you're a muon. A muon is a tiny unstable particle, like a heavy electron. They're created in the upper atmosphere when cosmic rays slam into air molecules, about 15 kilometers up. Muons travel at 99.9% the speed of light, but here's the thing, muons have a very short lifetime. They decay in about 2.2 microseconds. At the speed they travel, they should only cover about 660 meters before they fall apart, and yet we detect them on the surface, 15 kilometers below where they were created. From our perspective, their internal clocks are running slow time dilation, so they live long enough to make it. That's the time dilation explanation. But here's what's beautiful. From the muon's perspective, it lives for exactly 2.2 microseconds. It doesn't experience any time dilation. But the 15 kilometers of atmosphere it has to travel through, that distance contracts. From the muon's point of view, the atmosphere is only about 600 meters thick. Both explanations, time dilation for the Earth observer, length contraction for the muon, give the exact same result. The muon makes it to the surface. The universe is consistent. Relativity isn't two effects. It's one underlying geometry seen from different angles. The universe is not rigid. Space itself is flexible, negotiable, dependent on the frame of reference. There is no fixed ruler against which all distances are measured. There's only the relationship between observers and the one non-negotiable constant, the speed of light. Now we arrive at the most famous equation in history, and I want to tell you what it actually means, because the way it's usually explained is, I'll be honest, a little bit boring. E equals mc squared. Energy equals mass times the speed of light. Squared. People say it means mass and energy are equivalent, that you can convert one to the other, that nuclear bombs release energy by converting mass. All true. But the why is more beautiful than that. When you push on an object, when you accelerate it, you give it energy. As it goes faster, it gains energy. But as you approach the speed of light, something strange happens. The object gets harder and harder to accelerate, not because it's tired, not because of friction, but because its effective mass increases. Energy and mass are the same stuff, wearing different hats. The kinetic energy you're pouring into the object is showing up as increased mass, and c squared, that's a staggering number, about 9 times 10 to the power of 16 in SI units. That's why even a tiny bit of mass contains an enormous amount of energy. 1 kilogram of anything, a brick, a banana, a person, contains as much energy as about 21 megatons of TNT. The sun converts about 4 million tons of mass into energy every single second, via E equals mc squared. It's been doing this for 4.5 billion years, and it'll keep doing it for another 5 billion. All because mass and energy are the same thing, related by a constant, the speed of light, that appears squared. Mass isn't stuff. Mass is energy in its most concentrated form. The universe doesn't have two separate inventories, one for energy, one for matter. It has one, and the exchange rate is c squared. So why can't you go faster than light? What happens if you try? Imagine accelerating a proton. As it gets faster, it gets heavier. Remember, kinetic energy adds to effective mass. At 99% the speed of light, it's about 7 times heavier than at rest. At 99.9%, about 22 times. At 99.9999%, over 1,000 times. To reach the speed of light, you'd need to pour infinite energy into it. Not a lot of energy. Infinite energy. And the universe, as far as we can tell, does not have infinite energy to offer. The speed of light isn't a wall. It's an asymptote. You can get arbitrarily close, but you can never arrive. It's like trying to become perfectly cold. You can keep approaching absolute zero, but you can never quite touch it. Light travels at c precisely because it has no mass. It doesn't need infinite energy to reach c. C is its natural state, its only option. A photon isn't accelerated to the speed of light. It's born moving at the speed of light. In fact, a photon has no experience of time whatsoever. From its perspective, if we can use that word for something that never has a rest frame, it's emitted and absorbed instantaneously. The entire journey across the universe happens in zero time. Only for us, the massive observers, does the photon seem to take billions of years. The speed of light isn't just a property of light. It's a property of space and time themselves. It's the rate at which cause and effect can propagate. Nothing, no signal, no information, no influence can outrun it. Not because we haven't built a fast enough rocket, but because the architecture of the universe won't allow it. So let's go back to the train. You're at half the speed of light. You click on the flashlight. From the ground, the beam goes at c. From your seat, the beam also goes at c. But how? Because the universe adjusts the books. Your time runs slower, your meter sticks are shorter, in exactly the right amounts to make sure, no matter who measures it, the speed of light comes out the same. The universe will contort space and time themselves to protect the constancy of c. What light speed does to reality is this. It tells us that space and time are not a fixed stage on which events play out. They're dynamic, flexible, interwoven into something Einstein called spacetime. And the speed of light is the seam in the fabric, the constant that holds the whole geometry together. I'll be honest with you, nobody fully understands why this is true. We don't know why light moves at the speed it does and not some other speed. We don't know why the universe has a maximum speed at all. We just know from experiment, from measurement, from decades of testing that it does, and that every consequence of that fact checks out. And I think that's actually the most honest and wonderful thing about physics. Not that we have all the answers, but that every time we look closely, we find the universe is far stranger and richer than we imagine. And the strangeness isn't something to fear. It's an invitation. That's what light speed does to reality. It makes reality more interesting than it had any right to be.